Paris, and also I want to thank Paul Paris for interesting discussion about this work. So maybe some of you remember that I presented one part of this talk just the beginning during the first session in 2011. So I don't want to be focused on many equations today. I want to be focused on the main idea and the results. So as you know, the key factor for crack propagation is the stress intensity factor, but many times, even if the test is carried out at room temperature, nobody is considering the effect of temperature, even if there is a strong heterogeneity of the temperature at the surface of the specimen, because there is dissipation in it. Dissipation is located in the crack tip, in the reverse plastic zone, and we will see that this temperature field will create heterogeneous thermal stresses that can be considered in the stress analysis. So the important point is that the stress state around the crack tip is affected by the temperature. So the aim is to consider it in the computation of the stress intensity factor. So a lot of works have been published in literature about how to quantify the plastic work per cycle under cyclic loading. So there are famous papers by Paris, Rice, Rainer Pippen, and so on. But I didn't find any paper about the consequence of this plastic dissipation in heat. I mean, what is the consequence in stresses and in temperature. So the most important results of literature is that the plastic work per cycle is proportional to the power 4 of delta K and independent of the loading ratio and independent also of the loading frequency. So the plan of the presentation is, I will continue a little bit the introduction after presenting you the plan. We will see three problems. A theoretical problem with an infinite plate and a semi-infinite crack without any convection, any loss by convection. And after we will see two problems with the first one, a finite disk with a semi-through crack with convection. We will see the effect of heat loss by convection. And after the identification, comparing the real experiments and the finite element analysis, we will see confusion and prospects. So as all you know, probably know that the reverse cyclic plastic zone can be easily computed by or assimilated with the classic equation with the delta K power 2 divided by the yield stress power 2. And we can consider, based on literature, that the heat free within the reverse cyclic plastic zone is proportional to the radius of the reverse cyclic plastic zone to the power 2. And during the loading cycles, this dissipation will create thermal stresses. So now we will study the consequence of these thermal stresses in three cases, as I presented to you. So the first case is purely theoretic, with infinite medium under mode 1 loading. The second one is a finite disk with a radial crack with heat loss by convection. And the other case is a real experimental problem that has been solved by a finite element thermomechanical analysis. In all cases, the hypotheses are the following. We consider that the reverse cyclic plastic zone is small and the heat source is located within this zone. We consider that the crack is moving slowly compared to the characteristic time of the heat transfer equation. So it means it's a stationary regime with a thermal point of view. And we consider that the heat dissipation is constant per cycle. And about the constitutive behavior of the material, we have considered that outside the reverse cyclic plastic zone, the material is isotropic and thermoelastic. And within the plastic zone, it's perfect plastic. And we have solved both in plane stress or plane strain. I presented only plane stress conditions, but it's possible to solve within the two hypotheses. So in fact, the problem is a superposition outside the reverse cyclic plastic zone of two problems. The first one, which is the mechanical classic problem that you know. You obtain the stress intensity factor, I have written cyclic, I mean due to the cyclic loading. This is a classic stress intensity factor. And there is also a correction term due to temperature, which is due to the presence of the heat source at the crack tip. Of course, this decomposition is valid if macroscopically there is only a very localized plastic zone and if crack closure is neglected on the size of the plastic zone. So what are the most important results? Since I have not a lot of time, I will not show you a lot of equations, but analytical equations exist for the theoretical problem of the infinite medium. It has been published in 2011. And the most important results is that here, I'm sorry because the sizes are very small of the letters, but here this is the temperature versus the radius in front of the crack, so temperature here. You see there is a very big gradient of temperature, and this gradient of temperature that has been computed for the unit flux of 1 watt per meter creates thermal stresses, not residual stresses. So thermal stresses that is negative. So it means thermal stresses compress the crack tip because of the thermal expansion of the material. So we will compute the consequence of these thermal stresses on the stress intensity factor. So this is an analytical solution, but it's not a problem of that. What is important to see that is that the coefficient for correcting the stress intensity factor due to temperature is proportional to the heat flux. So it means all the calculations have been done for a unit heat flux, and if we are able to identify by experiments this value, you can quantify the correcting factor. And what is the value? For instance, you see in this graph in vertical axis the stress intensity factor versus time. So this is for the infinite medium. So in this case, there is no stationary regime because there is no heat loss. So you are giving energy by the cyclic loading, and there is no stabilized regime because there is no loss of energy. However, we can see that the correction is small. For a unit flux of 1 watt per meter, it's around -4, 10 to the -3 megapascal square root meter. So the key factor is how to quantify this heat flux. Now I'm presenting another problem which is closer to reality, that is a finite disk, close to a CT specimen, but the disk is easier for an analytical solution in polar coordinates with a semi-radial through crack, and this disk is loaded in tension, mode 1. With the solution, we have considered a classic heat loss of 10 watts per square meter per Kelvin. That is approximately the conditions of a test in a laboratory without cooling system. And you can see here for a steel, for its classic steel, you can see for different heat loss conditions, for 1 watt, 10 watt, and 50 watts, you can see the temperature evolution versus the radius. So here, the unit is a microkelvin, so it's very small, it's 25 microkelvin, but don't forget that this is computed for 1 watt per meter. So if you multiply here, for instance, by 100 or 1000, here you obtain 2.5 degree or 25 degree, which is more or less what we observe in experiments. And in this graph, you see the circumferential stress, sigma theta theta, versus the radius. And again, this is in compression, so it means that the crack tip is compressed a little bit by the thermal stresses. And with these solutions, since we have considered the heat loss, we have computed the evolution of this correcting factor, K1 temperature, for different coefficients of convection. In that condition, it's between 5 and 20 watt per square meter Kelvin, and we have computed up to 100, but you can see that the effect of the convection is small. It's varying between -0.6 and -0.5. So in fact, we can consider that convection is not very important on this correcting term. And now we have compared the profile of temperature with the theoretical problem computed by finite analysis from real experiments. So the experiments have been done on a construction steel C40 with the center cracked specimen under tension. So we have pre-cracked the specimen and we have recorded the crack evolution versus the cycle, and we have measured the temperature on the surface with an infrared camera in order to measure, to identify the dissipation. And the loading frequency was 100 Hz. So on the left, you can see the typical infrared measurement. So this is the electro-erosion crack. After there is the natural crack that you cannot see because of the resolution, which is not good enough. And the crack tip is at this point, and we measure the temperature a little bit in front of the crack outside the reverse cyclic plastic zone. And you have here the evolution of the temperature versus time for the beginning of the test. There are several tests and some tests with the stabilization of the temperature. But I show you this because with this decreasing, here we stop the test, and with the measuring of the decreasing rate, we are able to identify the heat loss by convection. And with this measurement, we are able, in order to consider both the dissipation and the heat loss. So what is important to see is that the mean temperature variation a few millimeters in front of the crack is 2.5 degrees Celsius. And with this 2.5 degrees Celsius, we can identify the dissipation. So this is the assumption for the finite element analysis. So we have modeled a quarter of the specimen with convection within all the surface except convection at the crack lips. So we have solved the classic equation of heat conduction, and we have considered so the convection everywhere. What are the results? So on the left, you have the temperature field, and on the right, this is the temperature evolution versus the x-axis, and you can see that at the crack tip, so the crack tip is here, you can see that there is a big temperature gradient, and this gradient will create the thermal stresses. So with this temperature measurement far from the crack tip, we can identify the heat flux, which is around 150 watt per meter. And with this flux, we can recompute the stress intensity correction. So before to show you the stress intensity correction, here you have the normal stress at the crack tip. So this is the crack front, and you can see the pattern of the stress field. And here again you see the crack front that is under compression with a -6 megapascal here. So with that, it's possible, with knowing the dissipated power that is around 160 watt per meter, in our test conditions, that is the stress intensity factor range of 20 megapascals per root meter, we obtain a correcting factor of 0.3 megapascals per root meter. So this is not an important factor, 0.3, but it's important not to forget that in our testing condition, the frequency of the loading is around 100 Hz. The test has been carried out on a vibrophore machine, but if you look at the components, for instance, that is vibrating at high frequency, like turbine blades, for instance, or any components loaded at a higher frequency, the dissipated power is proportional to the frequency, so the correction factor will be higher. So what we can conclude about that, first, because of the dissipation in the reverse cyclic plastic zone, the temperature field is heterogeneous and creates thermal stresses. So the classic stress intensity factor has to be corrected by the factor depending on the temperature and on the heat flux. An important point is that the range of the stress intensity factor is not affected because it's an additive term, but if you look at the ratio is affected. It means that if you compute the stress ratio with the stress intensity, Kmin over Kmax due to cyclic loading, it's not the same because of the temperature correction. So locally at the crack tip, the loading ratio is a little bit different. We have shown that the correction due to convection loss is not very important, not significant. And in our testing conditions, the correction is small, but because of the test at 100 Hz. and because of this material that is not very dissipating. So I believe that in prospects it's interesting to quantify systematically the heat flux within the reverse cyclic plastic zone. We are talking a lot of digital image correlation, but it's also easy to measure with infrared cameras the temperature field. So it's easy to identify the heat flux within the reverse cyclic plastic zone. In literature, there are many papers about thermoelasticity, which is also used to compute the stress intensity factor. But we can also use not the thermoelastic effect, but the dissipation to recompute that. I think it's interesting also to consider different types of material with different cyclic loading, cyclic behavior. I mean, if there is a cyclic softening, for instance, probably the dissipation will be higher. And in this case, I imagine that the material will behave significantly in a different way. And it should be also interesting to identify it on the viscoelastic materials, for instance, for polymers or composite materials. Thank you for your attention.